This is group SWI19. So here to present our large vision models for neurodevelopmental and from the child learning spaces. So my team members have Ibrahim Wai, interview Ernest, and then me, I'm interview Ernest, and then Tabitha Kebeti. So let us go. So that's our table of contents. We have introduction to the work, problem statement, research questions, objectives, research conclusion, method and systematic data, data description, results, conclusions, anticipated intention, and counteraction plan, references, and after document. So, according to adult education, like imagine someone like studying in a class like that image up there where students are they don't have like free learning spaces. So here child development ECDC. So brain growth and requires so like those people requires need a space where they can get where their brain can grow faster. Then the environment like learning that the environment like completes learning impact. That's why I said environment is called learning impact. So like I said, imagine like students up there, they are all scattered, and imagine students like following, like studying in this picture down here in the corner. So there you can measure who is going to learn faster. So current challenge like traditional classrooms, one size fits all. That's why I said like imagine that image up there, and then lack of child-centered design. So in Uganda we lack early child setup design, so that's why like most of the young children do not study very fast. So why generative AI automates design concepts, customizable age accessibility style aligns with safety and education guidelines. So that's why we are going to use our generative AI like to get those classroom designs. So the goal to support educators, architects, and policymakers. So here like we are supporting educators to come up with good class layouts and generate functional, but more appropriate spaces. So related works, recent trends and teacher review. So generative AI has recently been applied to various areas of design and visualization. Like text to image models such as stabilization and DLE have demonstrated the ability to produce realistic and creative images from contextual description, which has been explored in architecture and interior design for rapid prototyping and visualization. So in parallel, significant research exists on the impact of classroom design on learning outcomes, especially in early childhood development. Studies by organizations such as UNICEF, 2018, or ADC, UNESCO. So accessibility and use of color can influence attention, safety, and creativity in children. Academic work in environmental psychology also emphasizes that children's set of spaces improve engagement and learning. So, however, like while prior work addresses either AI-driven design tools or education space guidance, there is into researching on the AI introduction of generative AI with the domain-specific standards for classroom so environment. So recently AI was used like to generate various images, but there is no research about like added like classroom environments, like standards on classroom environments. So this project aims to bridge the gap by leveraging generative AI to produce classroom design concepts that align with mental education and safety principles. So that's why we are coming out. So problem statements like the domain application problem, like designing child-friendly classroom is complex. So people like find it very difficult to like, design a child classrooms. So must consider age-appropriate learning spaces, safety, accessibility, and developmental needs. So we have to consider those things. So architects and educators they often rely on manual designs, which can be time-consuming and subjective. So for them, they consider manual design. So our conceptual problem was how to automatically generate classroom layouts based on design requirements, have the input text prompts, age group accessibility space, and also someone prompts in a prompt and then the output be visual classroom design aligned with education and safety standards. So the challenge is ensuring AI respects domain rules, realistic layouts, developmental appropriate design. So the challenge is like we have to ensure like AI respects domain rules and like it come out with the realistic layouts and environmental appropriate design. So this is our further like prompt AI processing, generated classroom design. So research questions and objectives like our question are how can AI generate development appropriate layouts? Which design parameters must AI consider? How practical are AI generated design versus traditional ones? Like how practical are those AI generated designs versus the traditional ones? How can stakeholders interact with AI designs for learning? Here, our main objectives were for like to generate child-centered classroom layouts from prompts, to model designs, following education and safety standards, to evaluate layouts for functionality and age appropriateness, to assist educators, architects, and policymakers in visualization. Like those are our main four objectives. Like have to assist educators, architects, and policymakers in visualization. So then research contributions and outputs. Like contribution, we developed AI system to generate child-centered classroom layouts from user prompts, built a novel data set, like built a nautical room from PDFs UNESCO, more Uganda, design guidelines. They conducted a full EDA distributions, cross-tabs PCA clustering. Then feature enabling implement like converting long noise description EG furnishings into standardized categories. Like our framework linking education guidelines to support AI with the data. So like we are linking education guidelines so a structured AI with data. So outputs are curated data set, full EDA results, presentation and documentation. Yes. Here we have the methodology and system architecture. Like the methodology, the collection data processing and model development, construction learning goals, child profiles, evaluation, technical accuracy, development validity, usability and child engagement, like generative. So the methodology is like what we follow, the steps we follow, then the snapshot, the system design structure that makes those steps possible.
Okay, so take over from my teammate. My name is Savitha Chebet, and I'm going to take you through the dataset description and exploratory data analysis or EDA. So for the dataset description, we'll begin by going through the title. The title of the dataset is Early Childhood Development, Classroom Design. And the sources of this dataset or the sources of data for this dataset were policy PDFs from reputable organizations such as UNESCO and the Ministry of Education, Uganda. So we got structured data from this and we passed the data from these PDFs into rows that we used in the dataset. So when we conducted the EDA or did an analysis, we discovered that the features that had the most missing values were the outdoor feature, followed by the teacher desk placement feature, then the student desk placement features. In which columns we realized that these provide clearer patterns for modeling and standardized rotation. The curious we noted with this dataset is that it's skewed towards global or US sources. And there's a high risk for bias because if you look at this project, one of the main intentions first is to have this produce classroom layouts that consider the cultural context. So this could be one of the main issues we have right now. So we're going to go ahead to have a look at some of the output results that we had. So when you look at this graph here that shows a distribution of layout types, this is actually univariate analysis that we conducted. We can see that the general classroom layout is actually the most dominant class here. So it's a most dominant class and the rest appear more rarely or have lower frequencies when compared to this. It's a similar thing with the enriched furnishings or equipment. When you go on to look at the distribution for the enriched features, like enriched furnishings, enriched lighting, and ventilations, you can see that they also follow a similar pattern. For enriched furnishings, we again see standard appropriate furnishings being the dominant class. In other words, this is having the highest frequency in the data set when compared to the rest. It's a similar thing for the enriched lighting ventilation. We see natural lighting, the class natural lighting prioritized comma task lighting where needed is actually the class with the highest frequency. And this just shows us that this is most likely the most common design approach that is used for enriched lighting ventilation according to the sources that we inquired from. When you look at the top 15 values for region in which we see, like we had concluded at the beginning, that the largest amount of data that we have comes from global sources, followed by the USA. From this, we can safely say that Uganda has the least contribution to this data set, which means that there's a lot of potential for bias, especially when we consider that we are in Uganda and we would also want the model to produce layouts or designs that are or that fit in the cultural context that we are in. So we're going to go on to try and interpret what some of these results mean. So we conducted bivariate analysis, and in this we had cross tabulations and heat maps. So what you see before you are cross tabulations, and to just try and help you interpret this, the stacked bars, for instance, in the graph that shows layout type versus enriched furnishings, the stacked bars represent the layouts, and the different color bands you see represent the enriched furnishings. From this, we can see that the layout that has the highest number of furnishings is actually the general classroom layout. It's very diverse and has a large combination of enriched furnishings when compared to like the other layout types for this particular graph. It could be a similar thing that we could say for the graph that is for region versus enriched furnishings again. We can see that certain kinds of furnishings are more popular in certain regions. We can see that the global bar graph, the global stacked bar actually has a very large combination of different kinds of furnishings. Then you have the USA followed, then you have me, Finland, Kenya, the UK, Canada, and Uganda. So this is expected because most of the data we got was from global sources, followed by the USA, with Uganda coming in last. So this is actually one thing that we expected, showing that this is actually consistent with the graphs that we had before. When we look at the heat maps here, the heat maps just practically help show us the dependencies between the different features. We can see that enriched furnishings is a moderate dependency between enriched furnishings and enriched color, enriched furnishings and, pardon me, that's repetition, zoning and layout type, and there's a moderately low dependency between desk arrangement and zoning. That's for the unreached features. It's almost similar for, okay, it's different, but for the unreached features, we do see that subcategory and category do have a dependency, a moderate dependency between the two of them. Zoning and layout type do have a moderate dependency as well. And then the next we can infer from is desk arrangement as well, and zoning do have a moderately low dependency, but it still exists. So when you look at these two graphs, they look pretty much the same in terms of the dependencies, the number of dependencies we have been able to recognize. However, the correlation heat map for enriched features provides us with better interpretability because the values are more structured. So that's the main difference we can speak about there. When you look at the chi-square test, we see that a number of the values are above 0.05, which is actually the threshold that was set for us to determine whether two classes actually have a strong relationship between them. However, we can still take note that there are about three features that actually do have a relation, a strong relation, a relation between them. We can see region versus that are not dependent on each other actually. Region versus enriched color is one. We can go ahead to see that region versus enriched furnishings is another, and layout type versus enriched lighting and ventilation. So the chi-square test just helped us take note of the given features that actually are more dependent on each other when compared to the rest in the data set. So we're going to go on to look at this at a higher level. PCA stands for Principal Component Analysis. And in this graph, we're able to identify certain clusters. We're able to see a few clusters forming. Even though the clusters not very clear because there are a few features that are actually shared between classes. So we're able to see from the PCA graph that there are a few clusters that we're able to recognize. However, some of them are not very distinct from each other because some of the features do share certain characteristics. So for instance, I could say certain classrooms from our data set do share certain features. So even though there's some structure to this, or this shows that there's actually some structure to this, there's no strong separability between the clusters we've been able to recognize because of the overlapping that's present. The next graph just shows us pretty much a similar thing, but with the clusters listed this time. So we're going to go on to look at what these clusters, or just have an overview of what these clusters are composed of. From this summary table of clusters, we're able to see that the global sources actually contribute the most to the four clusters that we're able to recognize, followed by the USA. So it's mainly the global sources, then the USA, which again goes to confirm what we're talking about concerning the cultural bias that is present in this data set. So From this, we are still able to again come up with a similar conclusion. The data set, the presence of clusters shows us that our data has some structure. And the fact that it has structure means that it means that the AI is going to be able to train better and train wisely and identify certain characteristics in the data set that can help it come up with the classroom layouts that we require for the output required for this project.
Okay, so for the model selection and deployment, simply we used the stable diffusion. Stable diffusion is just that pre-trained model. Of course, it is already trained on millions of data sets and images, so it already knows how to draw images. So we did not to train a model from scratch to train it how to draw images and so on, but rather we used this pre-trained using the low rank adaptations so that it can efficiently adapt to our domain. So our task here was just to make it adapt to our domain such that the images it generates are in line with our domain, not the outside world images. So of course we used the clip text encoder. This is just for encoding the text into embeddings that can be passed into the model. As we all know that these models, they do not use text, so they need a format that they can understand and process, and that is where the clip text encoder comes into play. So by using this, we ensured accuracy, computation efficiency, and scalability to make our model suitable for real world deployment. How is it enabling the computation efficiency? Through using this, the gradient checkpointing and mixed precision. Of course, this is just for reducing the memory such that it does not store all the information that is not required, that is not necessary at that particular point. Of course, this is all because of the space, the computation space. And even right now, even after using all of these, the memory is not efficient. So until now, the deployment and the evaluation process has not yet been completed because of the memory, as you can see here. So it is wherever we train, we reach a particular point of training and coming up with some good results. Now the memory crashes and an exception pops. So that is the problem we are still encountering up to now. But with time, we are hoping to improve in the near future. So this is how it moves, the demonstration. It should start from the user input. So it is the user input. First of all, you feed in a text, what you want. I need a classroom for this age group which has this and this, for example, just an example. So this text is encoded, as I said, using the clip text encoder, such that it is encoded into the embeddings that the model can understand. Then after that, the model first starts with generating the noise, of course the random noise. It generates the random noise, but this is not an actual pixel image, but rather it is generated in the latent space. So it is the unit, the UNET, of course that is the model, and that model, it is going to take in that random noise that has been generated by the model, and it takes in the other text. Remember, there is a text that is fed in by the user, that I need a classroom which appears, which looks like this and this, and it is going to take in that text, of course not in form of text, it is already encoded into embeddings, and it takes in this random noise. So it keeps on removing the noise through what we call the denoising. It is diffusion denoising. So it keeps on reducing that noise until the noise has been minimized. So at the end of it all, it is going to generate an output which is a clear image. So that is how the product should be functioning. Conclusions, of course, we are able to fine-tune the stable diffusion, though the training is not yet complete because of the memory issues. So, of course, our aim is to make it generate some images, though, as I have mentioned, we have not yet accomplished this, and of course, to be able to measure these metrics such as the loss, the PSNR, that is the peak signal to noise ratio, then this is SSIM, the structure similarity index, just to see how the image and the generated image and the actual image are looking like, the loss, the difference between the actual image and the predicted one. So they are just the metrics that we need to find out, that we need to get, such that we can examine the accuracy of this module. But all of this is going to be accomplished after solving the memory problem. So some of the limitations that we have encountered so far is a small data set, of course, so it cannot efficiently train this model. Of course, the images have the data set, of course, is somehow huge, but the images, the clear and appropriate images corresponding to each row are still few. So we are still generating more images such that we can enrich our data set for effective training. The computation resources, of course, as we have said, we are still encountering the memory stuff, and we are suggesting solutions which are going to make us succeed, of course. And the time constraint, of course, we have limited time for efficient and effective training of our model. So the next steps, of course, fine-tuning this large version model on enriched data set. As we said, we are still enriching our data set for effective training. We are trying to expand the database and comparing. So these are the next steps that we are aiming at in our project. So some of the acknowledgements from the lecturers, of course, the team members for collaboration of the data set creation, EDA, and modeling. Of course, without collaboration, you cannot accomplish it. This is not a task which can be accomplished by a single person. Of course, in summary, that is how the training process is